electric race car. If you haven't seen our first live stream yet, you can do so here at our YouTube channel. And if you have any questions during the live stream for me or for the engineers we will be talking to, you can ask them in the live chat. The audio was off in the beginning. We saw, so sorry for that, but we will just continue right now and hopefully everything will be fine. So if you have any questions, just put them in the live chat and we will answer as many as them as we get, as we can. And if we don't have time for all the questions, we will answer them afterwards in the comments. So don't worry about that. Before I introduce today's guests, I would first love to bring you along on our journey. So I would like to tell you something about Forze and also the team. Forze is a team that develops, builds, and races hydrogen electric race cars. 13 years ago, we started with a go-kart, as you can see here, the Forza 1. And right now we race with full-size race cars. And we do this because we want to promote the power and the potential of hydrogen, as we feel and we believe it will be an important part of a sustainable future. Last August, our latest car, the Forza 8, raced against professional race teams in the Supercar Challenge. And here you can see it crossing the finish line. And by that, becoming the first car to ever beat petrol-powered cars in an official race, as it became second in its race class. An amazing achievement. The team itself consists solely of students from the TU Delft that halt their studying for 13 months to work on this project. Here you can see the full-time team. Next to this, we are also joined by part-time team members who study full-time and part-time also work on the project to help out. These students get no financial aid, no credits we don't get any credits for studies. We do this out of pure will and motivation. I myself find it an amazing project to work on, to develop the future of hydrogen, but we can also develop ourselves as young professionals. So that's a really amazing feat. Since March, we've been working from home full-time to make the car even better. And it's great to see how far we've come with this project this year. But anyway, thank you very much for joining in on the live stream. We will give you more information on the design of our next car, the Forza 9. Due to the coronavirus, of course, we cannot hold a physical design presentation as of now, but this way we can explain you more about our design. We can talk to our engineers, and of course, you can also ask your questions. Last month, the topic was more power. In the live stream, we talked with Munir and Pranav, two of our fuel cell engineers, and they explained how the power system in the car works. We talked about how we get to 200 kilowatts of fuel cell power, and they also explained how a fuel cell works and how we minimize other losses to other systems in the car so that we can get as much power to the wheels as possible. If you haven't seen that live stream yet, you can do so here at our YouTube channel. So next month, we will talk about aerodynamics and cooling. And the month after, in August, we will talk about how we can put all of this power and all of these systems into the speed of the car. So that's also a really, interesting topic. Today, however, the topic is more hydrogen. Our next car, the Forza 9, will have more than twice the power than our latest car, the Forza 8, of which you just saw the pictures. So would that also mean we need more than twice the amount of hydrogen on board during a race? To answer that question for you, we would like to show you the video we posted on our social media last Friday. So 8.4 kilograms of hydrogen in total. That's an increase of not even 40% with respect to our latest car, the Forza 8, while well, you would expect an increase of more than 100%, right? To answer that question, we're joined by two engineers tonight. And first, I would like to get to know more about the simulation side of the story. How did we get to this number of 8.4 kilograms? For that, we need Martin Osowski. He's one of our simulation and control engineers. So Martin, could you explain a little bit about what you do at Forze, and please introduce yourself.
Hey, Jesper.
Hey.
Yeah, so my name is Martin Osowski, and this year I'm working full-time at Forza in the simulation and control department. Basically, what I do at Forza is develop computer simulations of our car, which let us essentially test the car before we actually build it. And so this lets us compare different designs in a computer model and gives us a lot of valuable information, lets us look at designs based on metrics such as lap time, efficiency, and hydrogen consumption. We do a lot of different types of simulation at Forza. So for example, we have a quite advanced driving simulator, which models our full car and actually lets our racing drivers try out different setups and give us feedback. And so on the screen right now, you actually see one of our engineers driving in our simulator. And next to this, we also do a lot of what we call 1D simulations, or sort of self-driving simulations based on detailed components in the car. On the screen right now, you actually see the programming behind our driving simulator and all the different systems in it represented by those colored blocks and all the different connections between the systems, all of which we model, and all of which comes together to give us a full model of our car. So basically, my average day at Forza involves programming these simulators, testing them, getting results, and then comparing our results against real life to make sure that everything is correct.
Okay, nice introduction. So Martin, basically you build up the car in a computer to test what works and also what does not, so that the other engineers can, based on your results, can build that design, so to say.
Yeah, indeed.
Okay, before we continue, could you maybe give us a quick refresh on how we use hydrogen in our car? Like, how do we power the car?
Yeah, for sure. So in our car, as was explained in the last live stream, we have two fuel cells that convert hydrogen from our tanks and oxygen from the air into water and electricity. We then use this electricity to drive the wheels of our car. Then next to the fuel cell, we also have what we call an accumulator, where we can temporarily store electric energy. It works pretty similar to a battery, but instead of a battery, we use supercapacitors, where the main difference with a traditional battery is that supercapacitors store less energy, but can charge and discharge at much higher powers. So basically, excess power from our fuel cell can go to the accumulator, or if we brake using our electric motors, we can charge the accumulator as well. And so you can see this in the schematic on the screen, which kind of shows the different power flows that exist in our car. And so you can see the power can go either directly from the fuel cell to the motors, it can go to the accumulator, and then back and forth between the accumulator and the motors, we can have this sort of charge-discharge behavior where we're discharging our accumulator to the motors to give more power, or we're charging the accumulator with the motors when we want to slow down or brake with our motors, essentially. And so basically this energy we store in the accumulator, we can use as a boost when exiting out of corners. You can see it as a sort of slingshot that lets us get a lot of advantages in overtaking cars when exiting corners. And I would say it's really the thing that makes our car so competitive on the track.
Mm-hmm. All right, so in short, we have those two fuel cells and accumulator that both work together to power the wheels. You talked about your simulations, but how do you determine? I said in the beginning, how do you determine you have to take that 8.4 kilograms of hydrogen on board for a 1 hour race if you use these fuel cells?
Yeah, that's actually a really good question and something we spent a lot of time on. So the amount of hydrogen we need to complete a race depends mainly on three things. The first is the amount of power we actually want to get from our fuel cell. The second is the efficiency of our car. And finally, we can also, our amount of hydrogen is also determined by our racing strategy. So for the first, if you want to have more power, naturally, you also just need more fuel. This basically goes for anything. If you want to drive with more power, that extra power needs to come from somewhere. On the other hand, if your system is more efficient, you'll be able to save hydrogen while driving at the same output power. Basically, not all the power produced by the fuel cell goes to the wheels. Some of it is sent to the many pumps, compressors, and computers in the car. In the end, though, what we want is to maximize the amount of power on the wheels, as that's really our driving power. And so if we can reduce the amount of power needed by these other systems, we can also reduce our hydrogen consumption while not actually affecting our performance. Finally, we can also tune our race strategy to try and use less power while keeping our pace almost unchanged. You could think of this as a type of drive smarter, not harder type of approach, where we try to distribute our power usage most effectively along the length of the track. For instance, we can reduce our fuel cell power in corners where we aren't accelerating and don't need the power. This way, we can kind of maintain our overall performance while reducing our consumption. And so for all three of these variables, we develop simulations of our car that allow us to tune power levels, change out components and control loops, test different race strategies, and so on. In the end, we can see how fast our car drove, how much power it used, and then based on this, we can calculate how much hydrogen we need.
Okay, so based on your simulations of power, efficiency, and racing strategies, you basically can predict how much hydrogen we should take on board.
Exactly, yeah.
Last episode we saw, we talked about power, we also talked about efficiency. So we quite understand that now, but this racing strategy, that's something new. We haven't talked about that yet. Could you explain us how that works?
Yeah, for sure. So as I explained before, our car has two main power sources, the fuel cell and the accumulator. The fuel cell is a sort of constant power source that consumes hydrogen to produce power. Basically, whenever you're putting hydrogen into the fuel cell, the amount of power you'll get out will be proportional to how much hydrogen you put in. The accumulator is a bit different. It has to be charged in order to have power, and it gets charged by either the fuel cell or by the electric motors. And we use this sort of charge-discharge behavior to provide large power boosts for rapid accelerations. Based on these two systems, our approach to saving hydrogen by race strategy kind of started by asking when and how these two power sources should be used during a lap, such that we can get the power that we need when we need it, but aren't using the fuel cell when it's not giving us much benefit. So basically not consuming hydrogen when we're not getting much out of that hydrogen. Basically, we wanted to find an optimal way of drawing power from the fuel cell and the accumulator in order to save hydrogen while not reducing our performance. And so where we found we could make the biggest difference was in how we distributed power during what we call regenerative braking.
Okay, so you're trying to optimize when you use the fuel cell and when you use the accumulator, because the fuel cell is more of a constant power source and the accumulator more of a dynamic power source, so to say.
Exactly, yeah.
Okay, and this regenerative braking, we haven't explained that yet. Could you, what does it mean?
Sure, yeah, I can give you an explanation. So regenerative braking works pretty similar to a dynamo on your bike, which is used to power your bike lights. On a bike, a dynamo uses the rotation of your wheel to actually generate electrical power and also causes some resistance to your wheel and slows you down. In the car, we basically use a much higher power version of this type of system and use the electric motors in order to convert the kinetic energy of the car into electrical energy, which we store in the accumulator. So basically, our motors can go two ways. They can take electrical power from the car and put it onto the wheels, but they can also take essentially the rotation of the wheels and convert that back into electric power. And so then that power we store in our accumulator. When we brake for a corner with our car, we basically try to brake as much as we can with this system, so regenerate as much with our motors and use that to brake as possible. And then we use that energy that we put into the accumulator in this way to get a large boost out of the corner.
So by braking, we get back energy that we can use after the corner. But how will this be used in the Forza 9? How will we use it in the new car?
Yeah, so the biggest difference with how we're approaching it now is in the new car, we're going to basically try to turn off the fuel cell during this phase, such that it doesn't use any hydrogen. By doing this, we're allowing the accumulator to be fully charged by only the kinetic energy of the car. So basically only through those electric motors, and allowing for more energy to be drawn in this way. So as you can see in the picture, whenever we brake for a corner, we recharge using our electric brakes, and then we turn our fuel cell power far back. And then so we ramp the fuel cell power back up when we leave the corner, combine this with a large power boost from the accumulator, and achieve our cornering acceleration in this way.
Okay. So in corners, you almost shut down the fuel cell to save hydrogen, And once you get out of the corner, you use your fuel cell again in combination with your accumulator to really get that boost out of the corner and overtake other cars.
Exactly, yeah.
Okay. It sounds like a solid strategy. It also sounds like a logical thing to do. But is it really, is it easy to implement, or are there challenges to it?
Yeah, I mean, it might sound quite easy what I just said, and maybe even like an obvious choice. But in our previous car, we were actually unable to use this strategy as the rate at which we could change our fuel cell power was too slow. Basically, once you get into the details of quickly operating a fuel cell, things get a lot more complicated. If we want to quickly reduce the power produced by the fuel cell, we need a very fast fuel cell control system. As when we change the power of a fuel cell, we also need to really quickly change the amount of air and hydrogen entering the fuel cell, as well as their pressures and all the other factors in the fuel cell, such as the voltage.
Mm-hmm.
All of these things are interconnected, and we really need to make sure that when we're controlling the fuel cell, that, for example, no pressure becomes too high and that we don't go beyond any other of the limits of the stack. And so this meant that from the very start, we had to consider how we would design all the systems that surround the fuel cell such that they could be very quickly controlled. Something which is actually a quite complex task. However, it does give us a lot of benefits in racing with regards to how much hydrogen we need to bring for a certain speed. And it's also something that gets developed for this sort of racing application where performance is really important for us. However, down the road, it's something that can be transferred to passenger vehicles, so passenger fuel cell vehicles, make them more efficient and run on less hydrogen as well.
Mm-hmm. Okay. Yeah, it's indeed nice. As you say, the difficulty not only lies in developing the racing strategy itself, but also making sure the components can actually implement that racing strategy. To recap, you're basically thinking about three things: the power we need, the efficiency of the car, and the racing strategies that maintain our lap times while using less hydrogen.
Exactly. So we managed to reduce the amount of hydrogen we need by making our system more efficient. For example, the fuel cell we're using, our compressor turbine, and all the other systems surrounding the fuel cell. Next to this, we also developed that racing strategy, which I explained, as well as all the control systems, which is really the complicated part here to make that strategy possible. Like this, and of course, with a lot of simulation, we think we'll be able to achieve the lap times we're aiming for while keeping our hydrogen use to a minimum.
Mm-hmm. We have a question from Mael Kes. He asked if we will implement four-wheel drive with one motor to drive each wheel. I don't know if we can. That's what motors we will use and how we will use motors is actually for another live stream. That's the fourth one in August. Yeah, because then we will talk about how we will implement the speed and transfer all the power to speed. So, Mael, that we will answer this question for you in August. You will have to wait, unfortunately. Sorry. Well, Martin, yeah, I mean, this was a very clear story. Thank you very much for joining in
Thanks for having me on.
answering all my questions. I hope everyone had many questions answered as well by your story and your answers. So thank you very much.
Cool. Thank you.
Yeah, goodbye.
See you.
So next to Martin, tonight we are joined by Tuur Knevels. Tuur is a mechanical engineer at Forze. And yeah, who to better explain what Tuur does than Tuur himself. So Tuur, please introduce yourself.
Hi, Jesper. Hi, I'm Tuur. I'm currently in the mechanical engineering department of Forze. And over the last 9 months, I have been working in this team on the development of the frame and the packaging, essentially making sure that everything fits inside of the car and that it is attached in a sturdy way. Okay,
well, welcome Tuur. Martin just explained how we got to the 8.4 kilograms and that we need not even, 40% of our more hydrogen to finish a race. How much hydrogen is that in total? Could you explain a bit?
Yes, in total that mounts up to 8.4 kilograms, and that will be spread over 4 different tanks. Now, that might not sound like a lot, but keep in mind that hydrogen is a gas and therefore has different properties than a normal fuel, such as petrol or diesel. After all, 8.4 kilograms is only the equivalent of 4 2-liter soda bottles. So yeah.
Yeah, okay, that does not seem like a lot, and even 8.4 kilograms, that's not much in weight. Is it enough to race for an hour, just 8.4 kilograms?
Yeah, actually it is. Like as Martin previously explained, we ran plenty of simulations, including our fuel consumption to complete a full race. So maybe to better show the potential of this amount of fuel is if we compare it to a normal or commercially available hydrogen car, such as the Hyundai Nexo. If you would put the same amount of fuel that we are taking with us in the Hyundai Nexo, it would give you enough fuel to drive from Delft to Paris and back. It would be a range of over 950 kilometers. Now, unfortunately, the Hyundai Nexo does not have as many tanks as we do, but it can still reach more than 660 kilometers on a single fill-up. So it's already coming close or even better than petrol or diesel cars.
Yeah, that's indeed pretty nice. And then, of course, a fill-up itself, refueling only takes around 3 to 5 minutes, and the only emission is water. So I would say that's a pretty nice sustainable vehicle. So hydrogen is very light. I don't think the weight of hydrogen, that 8.4 kilograms, was a challenge for you this year. But please tell me, what was the challenge you had and the challenge you face when you take hydrogen on board?
Yeah, well, like you mentioned, indeed, the weight is not a problem we are concerned with, at least not for the tanks, but the volume. So the density of hydrogen at atomic pressure is around 80 grams per cubic meter, compared to water or even air, which are 1,000 or 1.3 kilograms per cubic meter. Imagine that's quite a big of difference. So you need for a very small mass, you need quite a large volume to store it, take it with you. Again, maybe to put it in a better perspective, if we would take the amount of fuel that we are taking with us now at a normal ambient pressure, it would be the equivalent of 5 oil trucks. So even if we were building a race truck, we would still need 5 of them to complete the same race as we now do with one car.
Wow.
Now, luckily, we do have a solution to this problem. We can pressurize the gas, and we pressurize it up to 700 bars. That's around 700 times the normal air pressure, or as we mentioned in the reveal video, around the equivalent of 1,300 elephants standing on top of you. Now, we do this such that it takes up a lot less volume, and we're able to fit in our car, of course. And indeed, it might sound like a lot, a really high number, but keep in mind that these tanks are specially designed for this purpose alone. So we can guarantee a safe way of storing our hydrogen on our car.
Okay, so yeah, tanks with gaseous hydrogen under a lot of pressure. Could we maybe look a bit more at the tank? Could you maybe show us a tank?
Well,
what does it look like?
I'm glad you asked, Jasper, because I actually happen to have one with me right here.
What a coincidence.
It is exactly this big. And as you can see, it's not the smallest one. This is one, we have actually 3 of these in our next car, together with a 4th one that's even bigger. This exact model is actually also being used in a Hyundai Nexo, and the other tank we have is being used in a Toyota Mirai. And therefore, both of these have been designed and tested to the highest automotive standards. So we're pretty sure that they are safe enough for our car as well. Now, to maybe explain a bit more how these tanks work, I can explain it with the figure you can see on the screen now. These tanks exist out of 3 main parts. One is a metal layer on the inside that is meant to keep the hydrogen inside. As hydrogen is a very small element, it can seep through any material that is even slightly porous. So we need to have that in order to keep it leak tight. And secondly, there is the solenoid, which is an automatic valve that we use to get hydrogen in and out of the tank in a safe way, and which we also use for refueling. This you can actually see here on this end of the tank. It's rather small, but quite a sturdy, big piece of metal. And thirdly, there is the carbon layers around the metal inside that give the tank its strength, so that it can withstand this huge internal pressure. Now, for reference, the bodywork of our car is made of the exact same material. It's able to hold our entire car up during the complete race, but it's often only a few millimeters thick. Whereas on a tank like this, the layers are stacked up so much that I believe it's around 4 centimeters thick. In fact, it's the only application that I know of where it's being used in such a large quantity or such a thick way, so many layers. So yeah, that's what makes these tanks also so large, but also very safe. Now, you might also think, why do we take 4 tanks with us or so many hydrogen? Can we not refuel during the race? And we would gladly like to, but unfortunately, the infrastructure is simply not in place yet for us to do it. And we really want to race or build a car that can race and compete petrol cars. So if we can refuel in the future, we definitely will. It will make our car even faster and lighter. But for now, we still have to take all of the hydrogen with us.
Well, very nice. Thank you very much, Tuur, for your explanation. And that tank, will it be in the new car or? Yes,
actually, like from this tank, we have 2 more laying in the workshop and the 4th tank as well. So they are there and ready to be implemented as soon as the rest of the car is ready. Okay, nice. Yeah, of course, you mentioned it. Safety is a big aspect of using hydrogen. I see a question from Monica who asked, is it safe to put this much pressure in the tanks? I hope Tuur already answered it a bit for you. But we also have a video that we can show. It's a video from Professor Dr. Ad van Wijk. He's an expert on hydrogen. He will introduce himself as well in the video, so I won't introduce him much more. But we asked him his ideas on hydrogen safety, so have a look.
Hello, ladies and gentlemen. My name is Ad van Wijk. I'm Professor of Future Energy Systems at the Technical University in Delft. And today I want to talk about safety in a fuel cell car. As you know, a fuel cell car drives on hydrogen, and hydrogen is stored in these tanks at a pressure of 700 bars. Is it safe? You could ask yourself this question. But it is really quite safe. When you have an accident, for example, with such a car, and the tank is breaking and you get some fire near the tank, that fire can never go into the tank because at that pressure, it cannot go against that pressure of 700 bars. So the hydrogen goes out of these tanks, and the hydrogen is the lightest and the smallest element. And that means that it rises in the air with 72 kilometers an hour. So very, very fast it goes up. And it takes with it the flame and the fire, and what you see is like you blow out a candle. The fire is blown out because of the speed of that hydrogen. And therefore it's not safe, of course, but it is as safe as, for example, driving with a battery electric car, or even safer. And it is really much more safer than driving a gasoline car. Thank you.
All right, Tuur. I see that I have another question for you from Mael Kes. He asked, did you consider using a different way of storing hydrogen in the car? For example, with a metallic sponge? Yes, actually, during the conceptual phase of our design, we did investigate other options. In essence, there are 3 ways of storing hydrogen. One is gaseous, like we do. One is in a liquid form, or one is when it's infused inside of a solid, such as Mael is proposing. Now, all 3 of these are technically possible, but unfortunately, not all of them are as feasible to implement in a up and running car, or at least our car just yet. So for now, we still decide to go with gaseous hydrogen. But once these other technologies are hopefully in a more mature state and accessible enough for us to implement in our car, in perhaps a future generation of our car, we will definitely look into it again if it provides benefits. For now, we are still using gaseous hydrogen. Yeah, definitely. So that was all we have for you about tanks today. So let's move to another topic. Tuur, you also spend a lot of time on packaging this year. Can you explain what packaging exactly is and how it works?
Yes. So packaging is the way of making sure that essentially everything fits and functions inside of the car. Like we have many different departments and engineers within our team, and all of them develop their own systems and make sure that those would work or they are sized to the correct scale so they can provide us with the performance we need. But in the end, all of these systems also need to work together and physically fit together in the car. And that is where the packaging comes in play. It's packaging all of the parts inside of the car. Now we use this through, we do this through CAD software. We don't have all of the components ready yet. Some are still being designed, some still need to be produced, or some need to be delivered. So for that, we have 3D models that we can then virtually fit together to try and optimize the way they work on the car. So that we don't have tubes that are longer than they need to be or cables that are in the place of something else. I hope that answers your question.
Yeah, sure does. So we saw that the tanks are quite large, and well, we also have many other components in the car. How do you still make sure that the car is streamlined and aerodynamic? How do you pack this all together?
Yeah, like I mentioned, it's not the easy job. There's a lot of different components that we need to think of. It's not only the tanks, but we also need air filters, compressors, the fuel cells themselves. There's cooling cycles, a lot of small pumps, reservoirs, a lot of sensors and electronics that all need to be thought of, while also maintaining a good airflow both inside and outside of the car. Mm-hmm. So I'm not able to show the exact design yet. We want to keep that for a future full design where I can show really everything. But for now, I can provide you with this image you can see on screen that displays the main components we have for now in the rear of the car. See that it is indeed already quite full. A nice comparison maybe is to compare to packing your car for a family camping trip. There are many different bags and suitcases from different forms and sizes that you all need to fit in the back of your car. And it should all fit, but you can't just place it anywhere. For example, you want the heavy things to be on the bottom. Some things you still want to have easily accessible. And these things also apply in our car. You want to keep the center of gravity as low as possible. And some parts need to be maintainable or reachable, as well as many other things. Like certain components just need to be next to each other to function together. So there's a lot to be thought of, and it's a challenge indeed.
Yeah. So you do not only have to think about packaging everything very closely and efficiently, but also that we can still reach every single component, every important component, if we might have to replace or repair it, for example. It sounds like a pretty big challenge to make this all work.
Yes, exactly. Like mentioned, everything still needs to be reachable and maintainable. So you even need to keep in mind the order in which you assemble certain parts and in which you would also take them apart if need be. And you need to keep space for your tools to reach your components. Would be if you weren't able to get your screwdriver or your wrench to the bolt you want to tighten or untighten, it wouldn't be the best design. But those tools also have a awkward shape sometimes, so it is quite some tinkering to get that done right. But I think overall, looking at our progress, we are doing quite well. Everything is coming together in a nice way that looks quite optimal to me, at least. But also, I cannot wait to show you the design. In the future, hopefully in person, in real life, and I'm looking forward to that.
Yeah, I think we all do. All right. We have some more questions that we will answer after this live stream from Michael and Mel Kess, because this was the time we had today for answering questions. Yeah, thank you very much, Stuur, for joining in and answering all the questions. It was nice having you and having you talk about what you do every day. So thank you very much.
You're welcome. Goodbye.
Goodbye. So we discussed many things again in this live stream. I hope you liked them, from simulating a car to racing strategies and from hydrogen tanks to packaging. But we also have a small little extra for you, because what does this mean for you? What does it mean to drive a hydrogen electric car? Aren't you wondering what it would be like, what it would feel like? For that, we have another video from Mr. Ad van Wijk, who can explain this very well for you in his own hydrogen car.
Today, I want to talk about how it is to drive in a hydrogen electric car. As you can see, it's a normal car, and I start the engines by pushing the power button. And as you hear, it's also an electric car. You don't hear anything. So, what is it to drive in an electric car? It is like driving in a battery electric car, but the only difference is that the electricity is not produced from a battery, it's not coming from a battery, but it is produced by using hydrogen in a fuel cell, and that fuel cell converts hydrogen into electricity, and you have an electric engine that drives the wheels. And as you can hear, we don't hear any noise from this electric car. Also, the car itself, it is like you drive in a normal car. You have your dashboard with all the functions that you have in a normal car, and the only difference is a quiet, nice car. This is a Toyota Mirai, and as you maybe know, but Mirai means in Japanese future.
So thank you very much for watching. We hope you liked it. I hope you liked it. And that you thought it was a nice live stream in which we showed you more parts of the design of our next hydrogen electric race car, the Forza 9. I would like to thank Tuur and Martin for joining in. I would like to thank everyone behind the screens. And I also would like to give special thanks to Professor Dr. Ad van Wijk, not just for this time, but all the time when he helps us bringing hydrogen to the people. Questions, again, we did not have time to answer. We will answer in the comments below. This was it for today. I hope to see you next month when we talk about more cooling and aerodynamics of the car. Find out next month how our engineers solve these challenges and get to see more pieces of the puzzle of the Forza 9, the next hydrogen electric race car. Thank you very much. See you then.